All right. Good afternoon, everyone. Thanks for coming, for your interest in our presentation today. Today we're going to talk about some of the work we've been doing with Greg Taylor and Wong, Benjamin Avanzi. So some of us will talk at different points today. Last time we held an insight session that was in October last year, and we looked at some Australian data that we gathered under a certain project I'm going to talk about in a moment, and we investigated how much correlation there was in that data. And what we want to do today is actually talk about moving beyond correlation and talk about some of the recent developments in that space by us, but also a little bit by others. So we'll start with some more context. It's always useful to start with context. And then we'll talk about correlations, what we're actually talking about, how they're used in practice, at least in our understanding, the dangers of correlations, and a bit of a first conclusion about that. Before actually showing the developments, we want to talk for some time as well about how to model dependence. There's a couple of distinctions we want to make that we should also inform some of the conclusions we'll make later on, and discuss those as well. And then we'll present a number of projects we've been working on, and with case studies, all of them illustrated with real insurance data. Hopefully that should bring it to life. Right? So there's a little bit of theory at the beginning, but we'll try to jump into the practical and illustrations as soon as possible. And we'll conclude, of course. There's a couple of sections here that we're not going to really talk to. The first is a list of some of the recent references in dependence modeling. This is here only as a resource. The presentation will be made available after the session today. And so if you want to learn more or have some pointers as to recent references you might want to look at, then these are listed there. And of course, the end is just the details of all the references, which journal, what pages, and so on. Good, so we'll start with the context. Probably worthwhile spending a minute talking about the significance of dependence modeling in actuarial applications. You're probably all familiar with that. Otherwise, I suspect you wouldn't be here. I suppose you think that's an important topic, so that's why you're here. But still, just to summarize, they have an impact on determining actuarial reserves. Normally, these are defined as a quantile, typically 75% here in Australia, or a central estimate plus a margin, and that margin is likely to be impacted by the correlation of the dependence structure. And they also have an impact or have an importance in determining the risk-based capital, okay, for solvency assessment. So more specifically, how does it have an impact? It has an impact because when you aggregate risks that are not perfectly dependent, then you have diversification benefits. When one is high, perhaps the other one can be low. So on average, they are average, right? So this is this diversification benefit. And it's a really interesting and difficult problem because you don't want to underestimate the diversification benefits, otherwise you've got some lazy capital. When you're holding too much capital, then that's actually required. And if you overestimate the diversification benefits, then you're taking too many risks, too much risk as well. So it's not often in actuarial studies, or sometimes you've got problems where you need to be on the right side of the risk, right? It's okay to be a bit more conservative, but in this case, you actually don't want to. You shouldn't be on one side or another. You should be right, because if you're wrong either way, it's not good. So it makes it a harder problem, let's say. So a bit more about us. So we're working on a number of things, but a lot of what we do these days is related to a linkage project. With some of the details of some of the details of which are on that slide. So this is a project that's maybe I'll start from the bottom actually, which is collaborative. That's important between and jointly funded by the government, the industry. So we've got some of our partners here with Allianz, IAG, and Sandcor, and academia. The title of the project was Modeling Claims, Dependencies, blah, blah, blah. I think what's important here is that it's for insurance, and we want an innovative approach with stochastic processes. I just flag this at this stage. We'll talk about that again a bit later. And in the description, the summary of the project, you have that sentence at the beginning, where we want to better represent the fine, complex structures driving the significant dependencies relevant to an ERM in insurance. So we'll talk about those two elements a bit more later. So correlation. A bit of an introduction. I think it's probably good to make a link with, or link to our previous Insight session in October. The main conclusions we had was that correlation will depend on your model. Okay, depending on what model you use, what's left in correlation will change. And the other thing is that correlation happens as a result of real phenomena. And in fact, the more of those you can explain in the model, the least dependent your residuals will look like. So you'll have as much correlation as stuff you haven't explained in your model. And we showed that we could wipe away all the correlation from our dataset, the OC dataset that's for Allianz, UNSW, Sandcor, and IAG, the partners of that project. This is Australian data that they provided under this project. But the conclusion is not that the data is independent. That would be the wrong conclusion. On top of that, another caveat is that what you can use to explain the past data might not be available for the future. Maybe you can observe how many storms you had last year. And storms will have an impact on what's going to happen in the future. But whereas you could use it to explain the past, maybe you don't know how, well, of course, it's not maybe, it's for sure you don't know how many storms you're going to have in the future. So you still need a model for that. And correlation is all but one way of specifying dependence. And we had stopped really at that sentence or that statement last time, and we want to expand a bit more on this today. That there's more to correlate. There's more than just correlation. There's a few links here that you can check later on if you're interested. So just to clarify, by correlation, we're referring to the Pearson correlation, so that's the standard one, right? The one everyone is familiar with. And that's a measure of linear dependence. And that's symmetric around the mean. We'll see examples with graphs a bit later on as well. So it is tied, in fact, in essence, to elliptical distributions, a family to which the normal distribution and the student distribution belong to. And in fact, it completely specifies the dependent structure of the normal and student distribution. So if you know the correlations, you know everything about that type of dependent structure. So why then would you want to move beyond correlation? I'll give some examples a bit later on of when and how this could fail. But before, I just want to, to further motivate what we're doing, talk about a bit of practice, at least our understanding of how correlations are being used in practice in most cases. So when you're calculating risk margins for reserving, you can estimate the mean and variance for each line of business, then correlation metrics, and with this you can calculate the mean and variance of the total liability. Using method of moments, you fit a certain distribution to that, and then you get the 75 percentile. Now, we make assumptions about correlations. Sometimes people use those two matrices, Beta and Reed and Colleagues and White, that we also mentioned in our last Insight session. When calculating capital margins, then modeling is a bit more sophisticated in that you actually look at the distribution of the liabilities for each line of business, not just the moments. And then you assume a certain dependent structure between them, typically a copula or a T-copula. Then you perform a simulation with that, and with this simulation, that gives you a pseudo sample of the sum, and then you can look at how this behaves, what the distribution of that pseudo-sample. So what are the pitfalls of correlations? I think the best way to do it is with examples. This one we showed last time, I just had to show it again. So one thing is to assume high correlation or high dependence when obviously there shouldn't be any. The example here is the one we used last time, where you have two series. You probably can't read what's on the slide. But one of the series is the per capita consumption of cheese in the US. And the other one is death by becoming tangled in your bedsheet. And it turns out that the correlation between how much cheese you eat and the US population eats and how often they die by becoming tangled in their bedsheets, the correlation is actually 95%. So should you assume that they are perfectly correlated? Perhaps not. Right? The problem here is that there is a common trend. So the idea would be to try and identify that and then detrend the two things and see what's happening with what's left. Right? That's what we discussed last time, so I'm not going to spend more time on that right now. That's another example. So assume you had a sample of 2,000 observations, joint observations of X, Y, and Z, and you've got the following correlation metrics. So they look independent, and on top of that, all three random variables look perfectly normal, in that, I mean, normally distributed, with a mean of 5, and a standard deviation of 2. Okay, correlation doesn't look like they're correlated, but are they dependent? Well, you can look at the dependent structure. So those graphs, I don't know if you're familiar with that, but it's called an empirical copula. But it's really just a scatter plot of X against Y, Z against X, and Z against Y. And not just the value, not in dollars, but in terms of probability. So it's quantized. It's just transformed into, with the CDF. So it's on the 0-1 scale. So it's much easier to see what the dependent structure when you do that. And here you see nothing, right? They look really independent. So the obvious choice might be, well, let's model the sum with a normal distribution of mean 5 and variance 12. Okay. Why? Because you've got three normals of mean 5. If you take the sum of three independent normals of mean 5, the mean is 15. And standard deviation 4, so variance 2, so variance 4. And then if they're independent, the variance of the sum is 3 times 4, 12. So what could go wrong? Right? It looks like the right approach. Well, in fact, when you look at it, we know how those variables have been generated. And the histogram you have on the left here is the histogram of the real distribution of the sum, and the blue is the result of the normal, our normal assumption. And if you look at the CDF, it's a bit small, but the colors, I'm not sure if you see the colors well, but in the right tail, the blue one on top is the normal distribution, and the red is the actual distribution. So you see that if you're looking at the 99 percentile, for instance, you would strongly underestimate the quantile with your normal distribution. So what went wrong? So what's behind? What's behind is that all three random variables are normal. They're actually not only uncorrelated, but they are theoretically independent. The model we're using, they're actually independent. But the variable Z is a normal with a mean 5. But what happens is whether you move from the mean to the right or to the left depends on the concordance, what we call the concordance of X and Y. So if X and Y are both above their means or below their means, then Z will be above their mean, above its means. So if X and Y are together very high or very low, then Z will take that feature as well. Well, it will be actually higher than average. And otherwise, it's vice versa. So there is some kind of relationship here that depends on the concordance of X and Y. Theoretically, all those variables are independent, pairwise independent, but really the catch here is that they are not mutually independent. That's a very important thing, maybe take away, is that when you look at correlations, you only look at pairwise correlations. So not only correlation is just one type of dependence, but it's just pairwise. But you can have dependent structures that appear when you look at more random variables. So the mutual independence is not the same as, is much stronger than pairwise independence. So this is a scatter plot of the outcomes for x, y, and z. So you see a pattern. When you move from 2 dimensions to 3 dimensions, suddenly the dependent structure becomes obvious. So here we would have underestimated the capital. Let's look at another example. In this example, we actually have correlations in the data. It's still 20,000 observations and so on. And you find that x, y, and z are normally distributed with those moments, right? Almost perfectly, but they've been generated like that. So if you're fitting them, it would be obvious that they are, right? But that's not the point. Let's say they're normal. So the approach, if you're using the procedure I described before for capital, is, okay, you look at that, you fit the marginals, they're normal. Then the next step is you take a copula, and you will fit a T copula, let's say, because that's more sophisticated than a Gaussian copula, with that correlation matrix. This is just scatter plots. You see there is some dependent structure. X and Y are dependent, X and Z have some dependence, and Y and Z a bit more. Right? So let's see what happens if you fit the T copula to that, and what could go wrong. It goes really wrong. Right? It's really funny. In this example, the red histogram is the actual distribution, the real one, and the blue is what you get with the copula. You see that the red one is actually bimodal, and the blue is unimodal because you take a normal with a T copula. And in this case, what happens is that the blue tail is under the red tail. So in this case, by using your copula, you would strongly overestimate the capital requirements. Okay, so it's not always, doesn't always go the same way. But in this case, there is a dependent structure that the T copula totally misunderstands. So what did we have as a model? We also had a model of Z depending on the concordance of X and Y. You have the formula here if you want to check it out later on. So a last comment on that example. This is the actual dependence you assume with a T copula. And that's typical of elliptical or copulas that use correlations. You see it's kind of linear and it's symmetrical. You've got concentration on in that corner and that corner. And it's the higher the correlation, the more concentration you have. And you see this is really not the right shape if you compare with this one. That's the real shape. That's what the T copula gives you. So what? Correlation, I think it's important. Correlation is a symptom, and it's not a cause. It's like when you have a gastro. You might have fever or not, but the gastro is still there. So correlation will give you an indication of dependence, but it's just a symptom. Doesn't tell you what the dependence is and what the phenomena are. So correlation sometimes fails to be present. Okay, that's the gastro without fever. When the cause itself is present, when you have a dependent structure. So the main conclusion here is that you should look for the causes of dependence and model those first. Examples found in the last insight session and later on in the case studies, for instance, catastrophe events. That could be the cause of dependence. So you should model that directly rather than using a correlation. You can use correlation only as last resort, but only for the residual unexplained, what I call stuff, right? Because I couldn't find a better word because by definition you don't know what it is, right? But often there's something left that you can't explain, and you need to approximate it with some structure. And then correlation and the copula is probably an option. But you should do that only in a way that is consistent with the model that you used. So if you use correlations, then they should be consistent with how much you've explained. Remind you, the last insight session we started with a correlation of 0.6 and we ended up with 0, depending on what model you're using. So if you are to make an assumption about the correlation, it should be consistent with your initial model, or the model that it goes on top. And you should assess whether other dependence structures might be more appropriate rather than correlation. Okay, so that's correlation. I guess the point is, it's being used, it is useful, but in some cases there is a case to move beyond correlation. So before showing you examples, I want to talk a little bit more about modeling approaches. Okay. If you actually want to talk about modeling dependence, what are the possible approaches? And we'll make two distinctions. The first is between implicit and explicit modeling of dependence. So in implicit modeling, that's probably the one you're probably familiar with both without knowing the vocabulary you're really using, implicit or explicit. So implicit, here, the effect of the drivers of dependence are approximated via an abstract dependence structure. But that's typically the copula. Okay, I can give you a copula function. If you look at the function, you say, okay, fine, that's the dependence structure, but I don't really understand what this means. Right? You can show a graph, as I did, so you see whether it's positive or negative and what tail, but it's abstract. Right? It approximates the stuff that's driving the dependence. So it's often very quick to implement. It's often also necessary when you have that stuff you can't explain. But sometimes you can actually directly model the drivers. Okay, that's what we call the explicit modeling. So in this case, you know what the driver is, and you explicitly put it into your model. So you can identify it. You can use a finger and say, here's my source of dependence. So typically you have common shock models or inflation models. If you look at correlation between claims over a certain number of years, chances are they are correlated before you do anything because just of inflation. Right? So if you actually deflate them, you have in your model something that is explicit for that driver of dependence. Then catastrophe models, take them out and model them separately. So this modeling often simplifies projections for a number of reasons. We'll illustrate some of them later on. And on top of that, you can actually learn something about your business. Okay? If you actively look for the drivers of the dependence and you model them and you calibrate them to your data, then that might tell you something interesting about where your dependence is coming from. Maybe you can control it, increase it, decrease it, depending on what your risk appetite or whatever your strategy is. So that's the first distinction. The second one is micro versus macro modeling. There are different definitions for that, so I will give you one. So the macro modeling, I think the definition I have here is mainly in the philosophy. Right? In the philosophy, you look, okay, what am I interested in? Let's look at an example with research. Let's say development of claims over quarters. So what you're going to do is you look at triangles of quarterly data. So you aggregate the data into quarterly data and you model directly your quarterly data. So that's a macro model because the focus is on the aggregated quantities. Right? You just aggregate to whatever level of granularity you're interested in the final result, and that's what you model. So that's, let's say, the traditional approach. Sometimes can be inflexible. Sometimes can be very flexible, but the disaggregation as the first step can bring some inflexibility. Models are very well known, enjoy decades of experience and understanding. So if you develop them, if you improve them, you actually root your developments in current practice, which is a big benefit, right? Because then practice understands what you're doing, and also these are models we know really well and have been developed for many years. The micro-modeling has a different philosophy. It says, well, big data, period, time, you've got a lot of data, transactional data, and we can actually we have the data to describe the process at which things happen, okay, with which things happen now. Let's say claims processes. What date they occurred, what date they were reported, what date we've had the first payment, the second payment, change of case reserve, the closing, the reopening, we've got all that data. Right? We can actually model the process, the dynamic process of the claiming or the payments. So in the micro-modeling, you want to actually take that approach to actually model the process itself. Doesn't mean you should go to the second, right? Obviously not, but in terms of philosophy, it's a bit different. So in life insurance, micro models have been used for a long time for market models when you have multiple decrements. But this is now also coming in GI, and we'll have examples later on in the presentation. So it's still less developed because 20 years ago we did not have the data, we did not have the computers we have today. So, and we did not have the Insurance Act saying that you should have models based on your own risks, right? So there's a number of things that happened in the early 21st century that actually all encourage everyone to move towards that direction. It's very flexible because you really look at the process at which things happen, and it profits from all the data that is available. But it can be computationally intensive. So a bit of discussion. As explained earlier, you should probably have a mix of implicit and explicit modeling. Explain what you can explicitly, and have an implicit proxy for the remainder. Macro is generally easier, but micro should always be at least as good in terms of predictive power or precision, because you've got more data, you more information. If you don't do something stupid, you should have something that's at least as good. The question, though, and it's still an open question and we're working on it, is whether it's always worth the effort, because obviously it's going to be more complicated, more computationally intensive. Is it worth it? Right? So that we're working on that question. We don't really have a definite answer. We think that in some cases it's definitely worth it, in some others it's not, but to have the final answer to this will take us some time. So 2 last slides before going to the examples. In terms of the claims models, there's a formula here, probably familiar with. Just an example. So if you look at the classical compound Poisson model, so it's a model where you have a Poisson number of claims, okay, and so that's a random sum. One thing you might, and J is the line of business, and I is the number of the claim. So you could apply a copula to the aggregate S, but what that does not do is make a difference between what happens on the frequency side and what happens on the severity side. And the dependence is likely to come from things happening about N and things happening about X. And if you actually proxy it at the S level, who knows whether that's going to be the same next year? Who knows? On top of that, if you stick to the standard Poisson model, if you actually look at the N and X separately, the only way you can include dependence in frequency is having common shocks, so common events. And if you want dependence in the severity, then this can occur only at those common shocks. So that's extremely restrictive. So you need to move away and generalize this model, which is something we've been doing. Just bear with us for a few minutes. Last slide before the examples. The advantages of the stochastic process approach. I remind you we had that in the title of the project. Okay, there's a reason. There's a number of advantages. First, you can use individual data to fit the model. So that's very useful for dependence. Imagine if you want to look at the dependence structure of 3 lines of business for yearly data, for capital purposes. You can look at the past 20 years. 20 data points to fit a dependent structure is really limited. On top of that, it's almost impossible that your dependent structure was the same in the past 20 years and will remain the same in the future. So in other words, impossible. If you look at the process itself, and maybe you need only 2 years of data. We have actually an example later on where we fit the model with only 2 years of data. And it's very precise in terms of the dependent structure. Then you get time consistency. If you understand the process, then it doesn't matter if you want to look at the time frame of 1 year or 5 years. Often you don't even need to reformulate the model, because you've got a model for the process and you just change the time frame. It allows also you to identify spatial versus temporal diversification benefits. And I need to explain what I mean here. If you look at a process of claims over 1 year, okay, there's two types of diversification benefits happening here. One, let's say you might have business in New South Wales and in Western Australia. Okay, so that will bring some diversification benefits because it's not the same storms. Okay, that's the spatial diversification benefit. Now, if you look at your portfolio and just double its size, okay, in the next year, what you're going to do is in a way a temporal diversification benefit because you don't have more spatial diversification benefits. You just have more business. Okay, just volume. And this is something you can really easily do with a stochastic process because you just change the definition of time. Okay, rather than having 1,000 claims for a year, you say I'll have 2,000. And that's and you'll have a different diversification benefit for that different time frame. And that's really easily done with the stochastic process. In some cases, it's easier to aggregate. You know what's happening, so you just aggregate things. There's an opportunity to better, or at least explicitly model some of the phenomena that are actually driving the dependencies, or some of the characteristics of the claims, such as reporting delays, autocorrelation, over-dispersion, and so on. I really think now, I'm sure you're all really keen to see examples now, because it's all this theory and it's nice words, but then how do you actually do it? So that's the rest of the presentation, and I'll hand over to Bernard for that second half. Thank you.
Okay, thanks, Benjamin. Okay, so what I'll do now is to give a brief overview of some of the things that mostly we've been working on, but it should of course be noted that any research developments don't occur by themselves, they occur in a vacuum. So in the last section that Benjamin mentioned at the presentation, that you'll get also lists a lot of work that's done by others that's really matching or supporting what we do as well, or alternatives as well. So I'll talk about some of these recent developments, and then just to give you a brief idea of what we're doing there, as well as some illustrative case studies of these developments. The first one is I'm going to talk about this multivariate Tweedy model, which is really a macro approach, because although we think the micro approach is great, there are definitely going to be situations where using a macro approach would be quite a bit easier. Which is this first work we're working on. Now, for each of these recent developments, I've also linked the corresponding documents that you can access. Some of these have multiple documents you can find on the presentation file. So this particular project, what we're looking at is trying to look at a macro approach to reserving when you've got dependent lines of business. And so the inputs are the standard aggregated data, your triangles, and the aim is to have a model which is sufficiently flexible, so you're not really restricted in terms of the assumptions about what the claims look like. Standard work in the literature tend to look at things like focus a lot on log normal. You may not want that assumption, and also we want a transparent introduction of the dependent structure. Okay, so the idea here is we want to look at something beyond log normal, and one of the really good ones that a lot of reserving work or developments have looked at is the idea of the Tweedy distribution, which is a major subclass of the exponential dispersion family, includes a lot of the really often used assumptions, Poisson gamma and so on, and generalizes the plain vanilla chain ladder Poisson model. So this is a fairly rich class, has been studied a lot in a univariate setting, but in the multivariate setting, much less so. And so what we did in this project is really to say, how do we bring in a multivariate version of Tweedy in reserving with dependence? And the surprising thing is there are multiple versions of what you call multivariate Tweedy and multivariate gamma, so you actually need to look into that a little bit. The way we did it is we used some work by Furman and Landsman, who decided, well, you can have essentially the common shock type setup for Tweedy distribution, meaning that each cell in our case, for standardized claims, has a component which is coming from the common shock and an idiosyncratic risk. So it's a very transparent structure there. And it leads to a lot of nice properties, like you can see where the common shocks are, how it's affecting your mean, invariance, and covariances, and so on. And it's reasonably tractable with closed form results, so it helps with the numerical side of things. So we did the work looking at how to actually fit it to data, and the case study we did for this model was we used some data from the US, Pennsylvania National Insurance Group. This is from the Schedule P in the US. There's a number of reasons for using this data. One is that this is one which people have looked at when people study methods for reserving dependence. Now, this data set consists of 2 business lines, personal auto and commercial auto, as I mentioned in the US, over just under 10 years. Of course, first thing we do is, what is the dependence? Is there a common driver? Now, so we looked at accident. What happens if we allow for accident year and development year effects, noting that we do not have the micro data here. We find that the Pearson correlation, it's around 0.29, so it's actually fairly high. And we also looked at, was there a systematic reason we could attribute to this correlation? We couldn't really find any, so it's reasonably likely that we could treat this correlation as coming up from correlated noise. Okay. So we fit in model, and one of the things with using alternative assumptions is you need to develop fitting techniques. So we looked at MCMC for this, somewhat computationally intensive, but or doable. And we further validated our fitting performance by looking at what happens if you have simulated data sets. Everything went really well. And from that, we can forecast what you mean of your individual lines, and your variances, and the whole distribution, of course. Okay, using very fast simulation techniques. Just a few minutes, we can get the full distribution. So it's actually a fairly good technique. I'll show you the full triangle here of the outcome, but you can see the type of results we're getting when we apply this Tweedy model. Okay. So of course, this is a macro approach, which if we wanted to, let's go away from micro, we think this has quite a bit of potential. So some of the things that we found, that we learned from looking at this Tweedy approach is we think that it's actually fairly promising, because it looks at the Tweedy, a commonly used distribution. It's very flexible, a big class of distributions. You can interpret the mean and variance to try to get some insights on what's happening. And you can also extend this. You can have various calendar effects and accident year effects if you wanted to. And so we think this is quite promising. So that's a macro approach. But of course, Benjamin talked a lot about the idea that we want to look at the micro approach, which is using more of the data that you have, using the individual transactional level data, and not necessarily having to group it to quarters or years. And the next 3 developments, which is a number of different papers underlying these, all look at this idea of using a micro model. The first one is really talking about how to actually model dependence when you're looking at a micro level data. And on the modeling side perspective, in other words, you're looking at stochastic processes. How do you model dependence between stochastic processes? Because it's actually much less obvious once you look at stochastic processes when you go from random variables, which are the aggregate results, to stochastic processes. And one approach is this idea of Levy couplers. So this was first proposed by Tankoff in the financial modeling, in quantitative finance, has been looked at in operational risk, but until we've looked at it, people haven't really looked at it for the insurance side of things. So the idea is, it's similar to couplers, but couplers for random variables. Here we're looking at stochastic processes. So they're different things despite sharing the same name. But it is an approach, which I'll explain briefly in a second, that straddles a number of the advantages of a common shock in the event side, in the event frequencies, which tends to be extremely parameter intensive, especially when you go to 2 or 3 lines. It becomes you end up having more, perhaps more parameters, way more parameters than you want. versus the distributional coupler approaches, which tends to be non-time consistent, as Benjamin explained when he talked about implicit versus explicit. So just to summarize the benefits of this approach, it's relatively parsimonious. You reduce the number of parameters that you need quite significantly. It's time consistent because it's based on dependence on stochastic processes, so it scales up and down accordingly, and allows you to look at the effects on frequency and severity dependence, as well as using available data, and allows you to go from bottom-up approach to modeling where you looked at, say, you're happy with certain assumptions about particular lines, then you look at dependence. It allows you to do that, similar to couplers, but now in a stochastic processing. To just give you an idea of what this Levy coupler is, I'll just show you the simplest version of so-called Levy process, which we can use to model insurance claim counts, insurance claim counts, aggregate counts over time. So you've got blue and red, which are what's your aggregated payments up till different times on the x-axis. You'll see that there are cases where both lines have a claim together, so it could be some weather events causing both lines having some claim. You could also have cases where you've got something happening in one line, nothing happening in the other. All right? So dependence comes from, when you've got these compound Poisson processes, comes from two things: having the same event affecting both lines, and then also the magnitude of the severity from that event. So you don't need to worry too much about the definitions there, just the idea that you've got a coming event and then coming severities if you wish. Levy couplers, it looks at the following. For each line, you look at what's called the tau integral, which in a Poisson process is just frequency multiplied by severity, the survival function severity. Okay, so what's the probability of reaching a really high loss? And then it turns out there is a nice theorem which says that all the dependence, when you're looking at things like compound Poisson processes, can be modeled by saying, let's have the tau integral for each line. So this could be the first line of business, U2 is from the second line of business. You can actually group them together in under some function, which is this Levy coupler, and you get what's called the joint tau integral, which represents the joint events and joint losses for your two lines together. And turns out you can do that to model all your dependence in things like compound Poisson processes. So the concept, for those of you familiar with couplers, is fairly similar to couplers, except that you're now applying it to a stochastic process, not just a random variable. Okay? So a lot of the ideas follow through, but technicalities will differ a little bit. So you can also look at different types of Levy couplers, and so one of the things is we think that we need more types of different Levy couplers to choose from if you want to use these. So one of the contributions we did was come up with different types of Levy couplers, just to quickly illustrate the types of dependence you can coming from. The top left of the corner is essentially small events, small claims, common events. So you can see different types of shapes. I don't want to go into too much detail here. But what we thought was more interesting is, well, what if you actually apply this theory to real data? And so we did a case study applying this type of idea to some workers' compensation data that we got from the Swiss Workers' Compensation Company. And data set is a random 5% sample of the construction sector for 1999, and this is all fully developed by 2003, I think. And features two classes of claims, medical claims and daily allowance claims. A lot of the claims, of daily allowance claims, also have a medical claim, which is as you would expect, but not necessarily the other way around. So in this case, firstly, I note it once again, so you've got a common event, right? You've got one event affecting both type of claim payments. And if you look at the severity, so this one is the actual, if you just look at the log sizes for the daily allowances for the medical. This is the empirical coupler. If you want to look at the coupler of the joint severities, there's a clear dependence between the claim amounts, which you would expect. Right? So what we do is, well, let's apply this model to this Levy-Coupler concept, to this data, this workers' comp data, and we fit it using essentially a multi-step approach. The IFM, the idea is you look at the marginals, you fit them really well, then you try to fit the Levy-Coupler model, and then once you've got some indications, you run the full thing again, where you allow everything to vary. The idea is you get a good starting point by doing this IFM approach first. And we found that the fit was quite well. It also indicated, of course, you need to look at how you can choose between models. So you can look at the effects of dependence through frequency, through the event coupler, through the empirical versus theoretical tau integral. And these all fit really well. And remember, the idea is you get a method which fits the data reasonably well and is relatively parsimonious. Okay. Now I'll come back to some of the insights for this, because there are also some extensions that we've worked on since that work as well, which is what happens when you go beyond 2 dimensions. Right? The idea of Levy-Coupler is very simple. It's just how to group Poisson processes together, Levy processes in general. What if you go beyond 2 dimensions? Now, it's analogous to what happens when people use couplers. Right? With 2 dimensions, everything's nice and straightforward. Once you go to 3 dimensions, more intricacies come in, because you may have situations where dependence between one pair is fairly different from dependence between a different pair or groups in general. So you need to look at methods of allowing for that. Whereas the Levy-Coupler literature, this dependence between stochastic processes, up till that point has had very limited work, and most models have this idea of have this feature of exchangeability, where all the groupings have the same type of dependence, which we don't want, because when you think about your lines of business, there are always going to be ones that's going to be behaving quite differently. So how do we do that? Now the idea is to borrow from couplers, okay, but now applying to Levy-Couplers, so for stochastic processes. And one method is to use this nesting approach. Okay, so it's somewhat technical, but the idea is actually fairly simple to grasp. You can build a model, a nested structure, by saying, let's group one thing at a time. So in this case, you've got 3 lines, and you can group one first, and then once you've grouped this, you look at the 3rd line and the group Levy-Coupler between 1 and 2 together. So you nest it at one step at a time. In this way, you can construct different types of dependence between different groups. Now, this is just when you have 3 lines. If you've got 4 lines, you can get different ways of doing it. You can just extend this by one more level, or you can say you can group 2 pairs first, and then group the pairs together. And when you've got 4, 5 or more, it becomes more and more flexible if you want to. Now, one of the things is, I mentioned it's somewhat technical to look at the conditions to make sure everything's correct. One of the insights, though, is that the conditions that this construction places upon you also means that when you build your model, you need to look at the groups that have the most or highest level of dependence, roughly speaking, first, which kind of makes sense. That's what's going to matter. Okay, so in terms of dependence, so you need to look at that first. And so to apply this and to study what happens with this, we also apply this approach to this Danish fire data, which is very well known because this is widely available and it's studied a lot in dependence modeling for insurance. But what's interesting is most people look at buildings and contents only. There's actually a 3rd line that's in that data set, which is the profits line. Losses to profits. And of course, we need to do standard adjustments to data, which is fairly commonly done for this data set. You look at data which only exceeding some threshold. You homogenize it, so it's really a non-homogeneous Poisson, and remove 2 of the largest outliers because that was highly influencing some of the information. Okay. So, just to give you a taste of what the data looks like, so B is buildings, C is contents, C is profits. So you can see the types of event types, number of losses. So there are losses which are only unique to each of the lines, not to profits. So profits is a much smaller component. And in particular with the profits, anytime that profits you have a loss, it's only when it's with something else. It doesn't turn up on its own, right? And if you just firstly look at in terms of frequency, it's clear that the building content is going to be much more important, okay? Just because of much more claims together. You can also look at the severity, and here these are the pairwise empirical couplers. Again, this is building contents. There is some dependence there, also likely some between profits and contents. Building and profits, you're starting to get lower and lower amounts of data. It's harder to tell, but perhaps. But the idea is there is some dependence there, but looks like that there are different levels of dependence between the three lines. And so this is why we needed to use the nested structure, because if you try to just fit a standard exchangeable Levi-Coupler structure, it just doesn't fit well, because you're forcing the assumption that they are essentially pairwise identical, heuristically speaking. And so we built a model using nested Levi-Couplers to see what we can do. And so we needed to build it one step at a time, look at the marginals, and because we've got three things, we need to look at the order of nesting. And in this case, luckily, it's fairly obvious. Building and content is one that you need to focus on a lot. And then you need to look at the bivariate Levi-Coupler and then group it together using that nesting structure. If we had more than three types, if you had 4 or 5, then it becomes more complicated because you need to look at different types of nesting that you want to use. So we fitted using a stepwise approach, and the results were nice. As I mentioned, the exchangeable version won't be able to do this. And also in the fitting results, we also found an unexpected, and this is to be expected, you have a trade-off fitting the buildings and contents pair versus what happens if you compare with profits. And buildings contents pair is fitted really well compared to what happens if you look at buildings profits, which is again to be expected because that's what you're focusing on with its construction like a nesting construction. Which brings us to the key insights of the Levi-Coupler approach. Okay, so I mentioned a large number of advantages, and just to quickly rehash some of these, it is very parsimonious, especially when you go beyond 2 dimensions. It's time consistent because it's based on a stochastic process, so it scales up and down. It allows you to apply this micro approach when you want to look at dependence, which I'll come back to a little later today as well. As well as we've got some goodness of fit procedures and some models that you may want to use if you want to apply this approach to your company's data. Okay, so that's the Levi-Coupler approach, really the idea of how we can model dependence between stochastic processes. Now we continue with the theme of micro-modeling, and we're going to talk about a number of projects where we've been looking at this so-called Cox process approach to micro-modeling. Now, the idea behind this strand of research is we want to look at a micro, in other words, stochastic process approach using instead of a standard compound Poisson process, we want to use a compound version, ultimately, of a Cox process. The reason we want to do this is Cox process, and I'll explain the idea behind these in the next slide, is that this process, it can give you over dispersion, it can give you zero dependency across times, and also approach nicely allows for practicalities, including reporting delays and changes in exposure. And perhaps more importantly, it generalizes very nicely to a multivariate setting. Okay. Now, a lot of these properties, in particular over dispersions, zero dependency, and multivariate extensions, are properties which previous work that people have looked at in micromodeling doesn't allow for. When people tend to look at compound Poisson processes, it's good in some instances, but it can't give you over dispersion, it can't give you zero dependency, it can't nicely allow for multivariate dependency unless you've got particular situations where you've got common shocks. Okay, so we needed to look at a more sophisticated version of micromodeling, so we think that this would describe the real world much better. Now, the idea is this, okay? We have, you can think of a claim process occurring over time. You can start with Poisson, okay? But now we add one level of additional variability, being that your intensity, in other words, essentially your mean frequency over a period of time, instead of having that being constant or deterministic or known, we also treat that as being stochastic. That's the idea of the Cox process. You make your intensity, in other words, your frequency variable being, not variable now, it's a process, your frequency per unit time, we make that stochastic as well. Okay, so condition on this intensity, the arrival looks like Poisson. But of course, we're saying we do not condition on this. We're saying this is actually random. A lot of our work tends to focus on what's called the short noise intensity. And to give you an idea, this is what a short noise process looks like. It is the jump, and then it goes down, goes down. The idea is that this is a well-known stochastic process which it's not negative, so you want that, you don't want negative intensities. It also exhibits mean reversion. Okay, so your claim rates, essentially, your claim frequency doesn't blow up to infinity. It's also relatively tractable. Okay, so this is one we put a lot of work in and develop fitting procedures and estimation procedures and so on. And I'll talk about most of our work using this intensity. But it's worth noting there are alternatives. We've also looked at the idea of using regime switching, which is the other obvious candidate for these type of models, where the simplest version would be you've got periods where you've got low claim rates and high claim rates, and you're switching between them in some random manner. You can have more than just good or bad. You can have medium, it doesn't matter. The choice of number of regimes, there are a number of statistical techniques you can use, or you could just use based on your judgment. Okay? And one of the nice things is that this is actually very computationally efficient. Okay? But as mentioned, this is an alternative. We'll focus most of our work today on the short noise approach. So with the short noise approach, okay, remember the short noise is for intensity. Okay, it's really the mean claim rate, mean claim frequency, and we have to develop a likelihood-based estimation. Okay, so using a Young algorithm. We also need to allow for the fact that, sure, we've got a micro approach, but in the end, you don't want to go to per minute because that's not going to be accurate. And we also allow for joint estimation of your reporting delay and claim arrivals, okay, because that happens to actually make a significant difference. A quick case study was to apply this to some data from our partners. Okay, so this is from buildings and contents. For major insurer. Now we've actually randomly subsetted data to preserve some of the confidentiality. We allow for changes in exposures. We remove the catastrophe claims. So these are things that we have identified previously as things that will affect your dependence. So you may want to look at these separately. We also, for this particular case, we group things into weekly intervals just to allow for some of these seasonalities. So we apply our algorithm and fitting techniques. Okay, and so we actually, one of the nice things is the techniques essentially says, well, you've got a random intensity which you don't observe, but you can actually filter that out. So you can actually see what's happening, or get an estimate of what's happening to your claim frequencies over time. And we can also get a forecast. So we've just aggregated for quarters just for illustration. Of course, we've got much finer than that. So the upper triangle is, of course, your observed. Your lower triangle is your forecast, okay, which we have not rounded, of course. And this again, it's fairly fast. A lot of these models we end up needing to use simulation, but you can get all these results, means, quantiles, fairly easily. Okay, so you can get all of that. And of course, I re-emphasize the point that Benjamin made that when you've got a model, assuming you've got a reasonable model, which is why we're looking at this Cox process in the first place, the micro approach is making better use of your data, okay, compared to an aggregate approach. That's why we want to do this. Some of the key insights for this particular development in these sets of projects, we will look at this Cox model, so it allows for over-dispersion and zero dependency, risk exposure, and reporting delays, with the aim of having a more realistic, having a better model. Okay, you don't want to start off with a bad, unrealistic assumption. We developed estimation procedures, and we made the point that you need to be careful with estimating. You don't do it in multiple steps because reporting delays will affect your estimation of your arrivals as well, of course, which when you think about it makes sense, but people often look at them separately. And filtering, of course, gives you interesting insights about what's happening with your claim rates over time. Okay, so which brings us to the last recent development, okay, which is how do you model dependence using the Cox processes? Okay, here this is somewhat a number of works in process, so I'm just going to give you the main ideas here. So the Cox process, one of the benefits I mentioned is that it readily lends itself to dependency modeling. Okay, the idea is what's your source of dependency? Okay, as we mentioned in the October session, we've got systematic effects, we've got stochastic noise, and how do we do it? Right? That's the ultimate research question. Okay, not just for this project, but for dependency modeling on its own. Now, with the Cox process, this works really well because instead of saying you've got a one common event which hits two lines, which could be the case, but that's not the only possible reason for dependency. The dependency could come from the fact that you've got your intensities which are changing over time moving together. Okay? You got some type of common level of intensity between two lines. So the Cox process immediately allows for that because the variability is coming from the intensities. So you've got dependent intensity, it gives you dependent in your claim counts in the different lines. And one way of building that is use and there are a number of ways of allowing for dependent intensities, but the idea is you can build a model by saying each line, using the bottom up, each line it's a Cox, but you have dependence in the intensities, and with short noise you can apply a Levy-Coupler, as we mentioned before. And the idea is you've got some type of intensity, so I've got 3 lines here, you can say you've got 3 lines of business, these are the intensities, not the actual counts. The intensities, you can make them dependent using some Levy-Coupler, and then from these you can also allow for non-stationary components, like seasonality, and in the end you get a dependent Cox process. Now this is not the only way of doing it, but we think this is one way which has quite a bit of potential. And some of the key insights, as mentioned, it's still a lot of work in progress, as Benjamin would talk about as well. This approach we think has a lot of potential. We've done some analysis of data as well. It gives you a nice and easily use micro model to allow for dependency, allows both systematic factors and dependent stochastic noise through that dependent intensities. And what we're seeing now, it's fairly consistent with what we've seen in the previous analysis, where you need to be careful in that because your empirical correlations could be really misleading when you've got systematic drivers, so you really need to allow for them. And having this micro approach using Cox processes does allow you to account for these features fairly well. Okay. So this is some of the highlights about the recent developments that we've been looking at, as well as some case studies. And now give it back to Benjamin to wrap up. Yep.
All right. So summary and conclusions. That'll be short, so we can have some discussion and questions. So in summary, our team is interested in better representing the fine and complex structures driving dependencies. And we're interested in the stochastic process approach for a number of reasons we've given you before. And we're also interested in extending current methods, as we did for the Tweedy reserving method. So in this presentation, we discussed the relevance of correlation. When is it relevant? How is it relevant? Different approaches for modeling dependence. And we illustrated some of those with our research and real data. So there's 2 elements also in the title. You've got beyond correlation and you've got recent developments. So I've got a slide for each. For the beyond correlation one, as said earlier, we showed that in some cases you can model out all the correlation, But this does not solve necessarily the problem because it's a symptom, not a cause. So if you modeled it out, if you had modeled it out, doesn't mean that you necessarily understand the causes. It also depends how you've done it. Right? But if you model it out, then you have a better understanding. Correlation can work as a proxy for unexplained dependency drivers, but it can also fail, as we illustrated. So in some cases, it might be better to use a different implicit approach for explaining the non-explainable. Right? And our preference is for the explicit modeling of those fine, complex dependent structures. So that's why we're interested in modeling them. In terms of the recent developments, if you look at the macro literature, so the current literature on, let's say, resolving triangles, it still focuses a lot on the implicit dependent structures. The micro literature is still trying to get the univariate case right. And in fact, there's only one model we know, one paper we know about multivariate micro model, and it's ours. But we're still working on it, so maybe there are other people working on it. But it's that scarce, right? It's really fairly new. So in our recent developments section, we showed how to make the existing macro models move away from implicit to something that's more explicit. And we have developed an implicit and explicit methodology for combining the micro level models, especially in reserving. So that's the main application we've been focusing in those papers we've presented. So what are the next steps for us and for others? One is in the modeling of the severity for the micro models, because all those papers we've actually shown focus on the frequency, which is one part of this. It's only half of the story. It's when do you have claims and how many of them, right? But the severity is important too, and we've got all the data, and there's a lot to say about severity as well. So that's a big area of work that we are working on it, but obviously we don't have all the answers yet. Then there's some major drivers that should get some attention in terms of modeling, like superimposed inflation. How can we improve the existing models and also as components of the other models we develop? And there's, of course, the question of micro versus macro. Because micro, the more data you have, the more precise you should be. But the question is it worth spending all the effort having a complicated model for it? So there's only one or two papers we're aware of that looked at that, some level of rigor. We're looking at that too. For instance, all those papers that look at compound Poisson processes, but not Cox, for reserving, they're macro level models. But in many cases, we don't see the point because it's actually equivalent to chain ladder. Right? It's not because you make it look like a stochastic process that you have more in your model. You need to move to what we said, Cox, for instance, Cox, to actually have something more in the model that makes it worth it. But this is still an open question, and so we're also working on that. It's not just getting things complicated for the sake of it. You actually want to know when is it warranted. And that's it. I think we should open up for questions now. I'm just going to quickly show you the rest of the slides so you know what you're going to download if you want to download the presentation later. So there's a list of recent references. So we just, with the taxonomy, the type of things and the papers, you can look at it. And at the very end, you've got the list of references of where to download things. And, for our papers, we actually put in the presentation, I'm just going back to one example. Yeah, for instance, here you see it's blue. There's actually a link on it. When you download the presentation, click on that, and that will bring you straight to where the paper is. Right? So if you actually want to check it out. Good, so I think it's time for questions now. So thanks for your attention, and if you have any questions, the three of us are more than happy to try and answer those. Did we stun you? Yes, James.
So as you know,
Wait for the microphone. We've got people on the webinar, so.
hi, it's James Bassman from Allianz. So we're one of the participating insurers in this
Thank you.
study that you're doing, and we've provided you with the data. I'm very interested in this field of research, obviously, because we have to make assumptions on dependence for risk margins and for capital modelling. And as you know, a lot of those assumptions are now quite qualitative. So my question is, how far away do you think you are at this point from being able to rigorously validate some of those correlation assumptions using the methods that you've developed?
When you say correlation assumptions, you mean about dependence assumptions?
Yeah, dependence assumptions.
Well, it depends how far you want to go. I think the models we now have are implementable and arguably better than some of the methodologies that people use. So we probably we're very close to having a model we could use in practice with this multivariate Cox model. It's something that can be used.
So would you be able to look at an insurer's data set and be able to at least approximately say that the correlation factor should be, say 10% versus the currently adopted 20% for a particular class of business, and how certain would you be in making that call?
Well, we could assess that, but an important part of the answer is it depends on which model you use, because if you have a model that's very precise and understands all the drivers of dependence, then the correlation will be zero. But it doesn't mean that your end model has no dependence. It just means that you understood where the dependence came from. So you have a more precise model of it, but you can't make all those phenomena that drive dependencies disappear. The point of what we do is to try to understand them, and so we have a more precise modeling of it. But Greg and Bernard, do you want to add to that answer?
Yes, very tight. I think a direct answer to your question is in relation to, let's say, the Cox process. The dependency parameters that exist in that process are measurable now. They have been measured. And they have been measured against the Aussie data set. So, that work is done. I guess one point to make, though, in relation to this question is that the question really comes to two questions, because the issues concerned with risk margins are, I don't like to call them different, but there's a different emphasis on them between risk margins and capital margins, where capital margins are concerned with the tails and risk margins aren't. And from a theoretical point of view, the dependency structure within any of these models is the dependency structure. And it's defined, it's measured, end of story, but it might not be the end of the story if you're concerned with capital margins, because you have a specific interest in the tails, and so you may want to look at the problem in a slightly different way. And there may be questions about the data as well.
I guess for us, where this would really become valuable is where, we do have data and we do remove certain things that can be explicitly modelled to explain dependence, like inflation, catastrophe claims, for example. And then you've got this remaining stuff, which we know there is some dependence there, and we need to assign some level of dependence. And the difference in the capital that you would come up with based on using, let's say, 10% correlations, I know correlations are blunt tool, but need some kind of tool to impose dependence. The difference in capital between using something like 10% correlations versus 30% correlations is vast. And we don't know whether 10% is right or 30% is right, might be maybe both are wrong. And certainly based on some of the preliminary findings in your study, you haven't really been able to observe much more than single-digit dependencies or correlations in many instances. So the question is, at some point in time, it would be good to be able to use this at least as a high-level validation tool to, if nothing else, to be able to get a level of comfort with the assumptions in place, and then at some point further down the track to be able to actually challenge some of the conservatism in those assumptions to the extent that conservatism might be unjustified.
That question or not?
The question is, I suppose, do you see this getting to that point at some point in the next few years where you could use these techniques to, with a reasonable degree of certainty, be able to comment that, look, the current assumptions might be in, a multiple of 2 or 3 out from where you realistically should be looking at?
Well, I think the answer to that is yes. I guess when you have contending estimates of parameters, what should be done is to look at the bases on which they were derived. That can be done now as well. That's not to say, of course, that we can't do better in the future, but the resolution should be one of looking at evidence, I think.
Yeah, I mean, what something you could do is to look at past data, let's say 10 years, and so maybe you say you're using a certain model, let's say Cox, and you use that model and you look at the residuals, and you say, well, look, had we used that model in the past 10 years, the residuals would have shown zero correlation. So it seems that in our portfolio, an appropriate assumption for the residual stuff we haven't explained is 0% or 10% or something like that. So I think that's something you could validate with your own data. But I think a major point is that it depends on which model you use. So if you say this is the model we're using, and now looking at our data, this explains most of the dependence, so we don't need to make any assumption about residual correlation. You look at evidence, you can look at your data and make a case and say, look, our model is so good that we actually don't need to allow for any additional margin on top of what the model is yielding. Then also there's a caveat in that what happens in the future is different from what happens in the past, what I said earlier. What you can model in the past, where inflation is known, for instance, is different from what you can model about the future, where inflation is unknown. But if it's in your model explicitly, then you can use a model about inflation and defend it and say, well, it's been accounted for. I don't need to add a correlation. I don't need to add correlation to my calculations and the margin because of inflation, because I have accounted for it in my model already.
Could you turn the problem around and perhaps approach it the other way and say, well,
microphone, I think. Yeah.
Could you turn the problem around perhaps and approach it the opposite way by saying, well, if your level of correlation was indeed, say, 30 or 40% that you would assume between two classes of business, then using our techniques, this is what we would actually have to observe in the processes, and that's just not visible. So you can disprove certain levels of correlation with some sort of like a hypothesis testing type of approach.
I think that's something that could be done. Yeah, like a theoretical case study. So what would you need in a model to actually yield a 30% correlation? That's something we haven't really answered yet, but I suppose it would be possible. Sharon, yes.
Thanks, Ben. It was a very interesting presentation. In practice, when we're looking at questions of, in practice, when we are looking at the question of risk margins or even on the capital margins, and I very much agree, Greg, that there's not really a distinction. One of the issues is that the sort of building up the risk margin will consider the non-modelled part of the risk. So we'll consider the model error, as well as the process error and the parameter error part of the question. The current framework that a lot of insurers in the practice are using is the one that O'Dowd and Smith, as I'm sure you're very familiar with. Now, the thing that strikes me about the O'Dowd and Smith framework, and certainly when I've seen it applied, is that the non quantitatively derived part of the risk is often the dominating part of the risk margin. But also what also strikes me about it is that they're often the things that are highly correlated between different classes of business that you would consider in the Dowd framework. Particularly, you also have to consider correlations between those factors as well. And that's a whole another level of dependency that you add on top of any dependency that you can get straight from your data. Do you think that the approaches that you're following now are able to shed some light on that? I mean, for example, if you have a model that takes into account something that we normally would take into account as part of the model error, that we then have to reduce the amount that we're taking into account of when we're doing this additional framework on top of it, and have you looked into that as possible sources?
Yes, I think I'll let you answer as well, but I think there's two questions here. So can we account for it? Does it mean that, I mean, the first question is, if you take into account, does it mean you can reduce the correlation? I think the answer is yes. And have we considered those particular ones? Not yet, but we're aware of that. And one of the things we're interested in as well is how to define correlations based on qualitative data. Right? There's a lot of research done in other fields about how to translate expert knowledge into quantitative assumptions, and there's probably stuff to be learned from those fields in that space as well. Do you want to add to this, Greg, Bernard?
Well, I think the point is well made that model error is very much the odd man out in this game. It really hasn't been attacked in any quantitative way. There is the Dowd paradigm, which I think is a very good one in the absence of another. It would be nice if some quantitative version of that or some other quantitative version of model error could be produced. There are some contenders around, perhaps more in the banking industry than in insurance. They bear looking at. We haven't done it yet. There's other demands that have prevented that happening, but it may be worth looking at that. But I take the point that I don't want to say that this is a matter of fiddling while Rome burns, that one examines in detail the smaller part of the capital margin, but rather I guess it's a case of first things first. Learn how to build models of these things and how to look at dependencies between business segments, in the hope that if and when someone is able to produce a quantitative version of model error, that some of these ideas will translate to it. And that was one of your questions, but until we see what that model is, we don't know.
Other questions?
I can ask another.
Yeah, challenge it.
So one of the trends, and this has been perplexing me for a little while, one of the trends that we see, particularly in the pricing space in our industry at the moment, is the use of data analytics or big data techniques or certain types of algorithms to discover, in some ways, I think you could describe them as unexplained dependencies that are not taken into account of in the current, say, pricing framework. Have you thought about those? And it's interesting to me that those all have been applied on the pricing framework, but none, to my knowledge, are being applied in, say, a reserving type framework. Maybe because the pricing questions are more pertinent at this point in time, who knows. But have you thought about those types of techniques where you are augmenting your data? So you're not just taking your as you have at the moment, say, I don't know, numbers of claims and sizes of claims, but additional information about those and trying to use those types of techniques to data mine out of that correlations?
So I think the answer is yes. There's two hurdles. First is to have access to the data. So we need partners who are happy to share that data with us. And second is to get such a project approved from an ethics point of view, because then you start touching about characteristics of policyholders and also other types of data that are more personal. And it's generally harder, but it doesn't mean it's impossible. Right now we haven't done it because it would be a different project and we would have access to different type of data which we don't have access to at the moment. But we definitely discussed it, right? And if there's anyone out there who's interested in doing that and happy to share data and some resources, then we can set up a similar project for that. There's something you want to add?
Yeah, I guess there's a big question of motivation. You're going into the field of micro-modelling, and there has been some of it done in reserving. I guess anything that calls itself a statistical case estimation system is more or less what you're describing. But one has to consider the motivation. In pricing, your objective is to differentiate individuals, and so naturally there has to be great emphasis on introducing the variables that will do that. In reserving, you could do the same thing, and that's what the case estimation systems do. But for the simple problem of reserving, just to create a reserve, what would happen is that if you introduce that kind of differentiation, you produce differentiated reserves, but then in the end you just add them up to an aggregate anyway, because that's all that you need to know. You may have business reasons for wanting to know those reserves at a much more detailed level, and if so, that would be your motivation for doing that. But in reserving in general, there isn't the same motivation.
Maybe a last question, if any? I just would like to acknowledge the contribution of two people who are in the audience now.